Alright, hi, welcome back. Today we will be doing Transport 2, Homework 2. The situation that we're looking at here at the top left is a uniform cross-sectional capillary with two liquids, with H2O on the left side and D2O on the right side. And the positive Z direction we are going to define is this way, with the increasing centimeters. So there's a divider in the center, as you can see, and this splits it right down the middle, and it will be removed at 0 seconds. So the mass concentration for deuterium oxide is 1,110 kilograms per meters cubed, and the molecular weight for it is 20 grams per mole. And at a time of 0.1 seconds, the max molar diffusive flux is going to equal 2.78. So right now we want to look at the first question, which is, what is the overall mass flux corresponding to the maximum molar diffusion flux? Okay, so we have a net molar flux equaling 0. How do we know this? Well, because it's a closed system and no moles of water or deuterium oxide are going to be entering or leaving the system, and the volume is going to remain the same. So you know that here the net molar flux is going to be 0, here it's going to equal 0, and so on and so forth, because it needs to be uniform, and as they mix it, that statement will remain the same. So looking at this equation over here, as we substitute the net molar flux to equal 0, these terms will cancel out and go to 0, and then it shows that for the molar flux of water will equal the molar diffusive flux of water, and the same for deuterium oxide. You can also rearrange this equation, the top equation of the net molar fluxes equaling to the molar flux of H2O plus the molar flux of D2O, to set them equal to each other so that they're equal and opposite for the molar fluxes of H2O and D2O. But that doesn't necessarily mean that the net mass flux is going to equal 0, and I'll get into that later. But for right now, let's talk about converting moles to mass. So to convert from moles to mass, you multiply the amount of moles times the molecular weight for that specific species to equal the mass. So you can also apply this to our molar fluxes to get our mass fluxes. So the same approach is taken, and then we end up getting these values here, and then you sum those mass fluxes to get the net mass flux. And with that, I get negative 5.5 grams per meter squared per second. Okay, so now we're going to look at the second part of this problem. We want to make an order of magnitude estimate for the maximum driving force for diffusion at a time of 0.1 seconds. So this is the equation for the driving force, and I'm going to simplify this by making H2O equal 1 and D2O equal 2 for the values that I will use for I and J, just so it's easier to write into the equation. Over here, I'm showing that the summation of the molar diffusion fluxes are going to equal 0. And I can prove that using this given equation and simplifying it so that it equals 0. I did that in my last video also. But what's important is that we know that the molar diffusion flux for H2O and plus the molar diffusion flux for D2O equals 0. So if we move over here, we can see that the Stefan-Maxwell diffusivity is going to equal 10 to the negative 9 meters squared per second. And that's because this is an almost ideal situation. So we can assume that it equals the diffusion coefficient. So I'm also going to calculate for the total molar concentration using the same concept with mass concentration and molecular weight. So just going from mass to moles is the reverse. So we're going to take the mass divided by the molecular weight to get the moles. And I showed that here, and you can see that the units cancel out, and you get 55,555 moles per meter cubed for the concentration of the molar concentration of H2O. And then I did the same thing for D2O, and then I summed those together and I got this value, but then I divided by 2 to account for both the species in both sides of that capillary. And then I ended up getting 55,527 moles per meters cubed. So going back to the driving force equation, this goes to 0 for obvious reasons. The top cancels each other out, goes to 0, and 0 divided by a number is 0. Then we take the mole fraction for component I multiplied by the molar diffusion flux of component 2 minus the mole fraction of component 2 times the molar diffusion flux for component 1, all over the total concentration times the Stefan-Maxwell diffusivity. But we're going to plug in the value we defined up here, the diffusion coefficient, which we assume is 10 to the negative 9 meters squared per second, because it's they are both liquids, and that's a good estimate to use. So then we can simplify this equation by plugging in negative J1 for J2, because we also defined earlier that the addition of those two molar diffusion fluxes for both the liquid species will equal 0. So I plug that in, and then I also plug in 1 minus x1 for the component 1, because 1 minus x1 will equal x2. Those are mole fractions. The mole fractions of x1 plus x2 will have to equal 1. So then you can simplify that out, and you will cancel out a negative mole fraction of 1 times the molar diffusion, the molar diffusion flux of 1 will cancel out with the positive of the molar diffusion flux times the mole fraction of component 1. That was a tongue twister. So then you're left with a negative molar diffusion flux of 1 all over the total concentration, molar concentration, multiplied by what we're subbing in is the diffusion coefficient for components 1 and 2. So that gives me with this value of negative 50,066, which I can round to be 10 to the 4th for the driving force, because we're just concerned with the magnitude. The negative doesn't really matter here. So that would be a good estimate, would be 10 to the 4th for the driving force magnitude. Okay, and I think that's it for now.
So for this last problem, we are going to talk about the transport profiles. So initially here, we're going to have the time equal to 0.1 seconds and the final equal to infinity. So that's when we could consider the volume with both liquids to be uniformly distributed. And intermediate would be somewhere in that halfway point when the mixtures have not yet uniformly mixed, but have started to move past that initial concentration gradient. So first we'll consider the mass concentrations for water and deuterium oxide. So you can see here at the water, it starts at pure water over here, and then all of a sudden it hits this concentration gradient and goes all the way to 0. Really quick, it's a steep slope. And that's because the divider has just been removed, and so the liquids haven't been able to diffuse barely at all. So that's why it goes from pure H2O to then pure D2O, and that's where those steep slopes come from. Over here, this is where the water and the deuterium oxide begin to start diffusing outward more into throughout the set volume. So the D2O is moving to the left further, and the H2O is transporting to the right further. So that's why you see a less steep concentration gradient, and you can see that it doesn't just go immediately from pure H2O to then no H2O on the right side of that volume, of that capillary. And same for the D2O moving into the negative z direction, you don't see that immediate change from 1,110 to 0 mass concentration. And then the final, they are uniformly distributed, so it's at that pure 1,110 kilograms per meters cubed for the deuterium oxide, and then it's at that 1,000 density, pure density for water. And it's just constant because it's uniformly distributed at that point. And then we're going to look at the mole concentrations, and if you look at this, it's really similar. So it follows the same concept. So the water goes from a pure molar concentration of H2O to then 0 concentration, because there is no H2O on this side as of yet at 0.1 seconds. And same thing for the deuterium oxide. In the first half of that capillary, there is none. There is no concentration there. And then you see those less steep slopes because the liquids begin to mix throughout the volume, but not quite all the way that they're uniform until you get to this final stage. You see that it's finally hit that constant concentration of H2O and D2O throughout the entire volume. And now we look at the molar diffusive fluxes for water and deuterium oxide, and you can see this spike here in the positive direction and the negative direction. H2O is transporting to the right, so that's the positive z direction, and that's why it's a positive 2.78, and the negative z direction for the deuterium oxide. And this value was given in the problem statement. And they're the same because if you sum the molar diffusive fluxes for both the species, it should equal 0. So they're equal for H2O. The molar diffusive flux for H2O and deuterium oxide should be equal but opposite. Same concept over here is that the concentration gradient, the slope is not as steep because of that concentration gradient. The liquids have been able to move throughout the volume a little bit more, but not quite at that uniform state until you get to that final stage where there's 0 molar diffusive flux for either species because it's uniformly distributed and they're in equilibrium, both of the species. And then down here we're going to be talking about the mass diffusive flux, the mass flux, excuse me. And so we found these values in the first problem, and the mass diffusive flux for the net mass diffusive flux for this problem was negative 5.5 times 10 to the negative 3 kilograms per meter squared per second. And so we see that this goes down to the negative direction and peaks right here, and it's a really steep slope because that's at that concentration gradient yet again, and that's where that mass is really transporting from the left for the deuterium oxide and to the right for the water. But the net mass flux is going to be in the negative direction because the molecular weight for deuterium oxide is slightly greater. So for every 1 mole of deuterium oxide that's moving to the left, there's more mass moving to the left with it because of that higher molecular weight than the water. And then it becomes less steep over here because for the same reason, they've been able to distribute more throughout the volume, and there's less need for that mass flux to happen until you reach that final stage where the mass flux is 0. The net mass flux is 0 because it's the two species are in equilibrium and they both reach 0.